Hello guys. So again we talk about the hemoglobin. Usually most and I have some experience here. I have experience in Egypt and Gulf as well. So sometimes we are teaching hemoglobin and with respiratory system. Sometimes we teach hemoglobin with the circulatory. Here they are teaching some of hemoglobin with the blood, and you are going also to make some details, extra details about hemoglobin association curve with oxygen and the respiratory. So I try to make this summary which you can help you to remember it. So when we talk about the structure of hemoglobin, from chemistry you studied before, we say hemoglobin is kind of very complex macromolecule protein. Macromolecule protein means like it is from many subunits, and you can see here is 1, 2, 3, 4 subunits. So that hemoglobin is 4 subunits. Structure is 4 subunit, and each unit from that 4 subunit is from something called the heme and the polypeptide chain. Here is the heme and here is the polypeptide chain. Polypeptide chain is kind of protein. The protein name what we have in our hemoglobin is called the globin. So hemoglobin, so it is globin. And by the way, you should remember, generally we have the globin what we have, it is coming from 4 genes. You study that one polypeptide chain coming from one gene. We have this kind of globin, it's 4 polypeptide chain, and this 4 polypeptide chain, this is from globin, and we have 2 alpha and the 2 beta, and we have 2 alpha and the 2 beta globin. And the heme group, it is from something called protoporphyrin. That protoporphyrin, which is protoporphyrin and one central iron. So each protoporphyrin is from 4 ring called the pyrrole. So pyrrole, and one central iron ferrose. This iron is ferrose, not ferric. This iron is ferrose, not ferric. And here is the structure for the hemoglobin, what we need now. So we can say now, the heme and the globin are combined together in the mitochondria if osteoblast in the bone marrow. Remember osteoblast, So the heme and the globin come together in the erythroblast in the bone marrow. Then we're talking about the type of hemoglobin. Of course, we have many types than this one, but usually we discuss about here is the general types what we are written in most of the lectures. Adult hemoglobin, like the hemoglobin what you have and what I have, it is 2 alpha and the 2 beta. Differences between the type of hemoglobin mainly because difference in the polypeptide chains. 2 alpha, 2 beta, this is normal hemoglobin, we call it adult. And we have fetal hemoglobin, and that fetal hemoglobin contains 2 alpha and 2 gamma polypeptide chains, so there is no beta. But you should know after the birth, at the birth, this will be replaced gradually by hemoglobin A. So just remember this one. Hemoglobin fetus is the main hemoglobin at birth, and it will be replaced gradually by hemoglobin adult by the age of 4 months. We talk about the age of 4 months, completely the blood is hemoglobin adult. I hope I'm clear. Why we say this one? Something very interesting for you here is that this fetal hemoglobin has high affinity to oxygen than adult hemoglobin. Really? Yes. Why it has high affinity? Because this gamma has high affinity than beta. I will explain why later, but just to know, kind of what God gave us. Usually the fetus in the uterus of the mother, and the God gave him ability to be able to attract oxygen more than the mother hemoglobin. So in all cases, don't be afraid about your fetus in the uterus, because his hemoglobin or her hemoglobin will be able to attract oxygen more than the adult. We have some cases which is normal as well. Here is normal oxyhemoglobin. And please, this some people say oxidation. No, it's not oxidation. It is oxygenation, not oxidation. Remember it. Oxygenation, not oxidation. What difference, guys? Difference that oxidation, you will make oxidizing the ferrous to ferric. Oxidation means ferrous oxidized to ferric, and this is pathological case. But oxygenation, the oxygen will bind with the iron and remain ferrous. So the normal oxyhemoglobin, it is normal case when our hemoglobin bind with the oxygen, and remember, oxygen is attached to the iron which remain in the ferrous state. And each hemoglobin combined with 4 molecule oxygen. 4 molecule oxygen. I hope I'm clear. Okay, the affinity of hemoglobin to oxygen is great and decrease by something. يعني affinity of hemoglobin is great. Let me write it here. Affinity of hemoglobin to oxygen is great and decrease when, guys, in what? In very high hydrogen concentration, which means high hydrogen means a high partial pressure of CO2. The same meaning low pH or high temperature. Or if you have more from one material called 2,3-diphosphoglycerate. 2,3-diphosphoglycerate. Okay, guys, in RBCs. This 2,3-diphosphoglycerate will compete with the oxygen for hemoglobin. Okay, we will discuss about this also later, but just remember, oxyhemoglobin is normal, not pathological. But oxidation hemoglobin by converting ferrous to ferric, this is pathological. Carbaminohemoglobin, when we're talking about hemoglobin bind with CO2. So hemoglobin can attach to the CO2. CO2 attached to amine group of polypeptide chain of hemoglobin. Remember, CO2 attached to amino group of polypeptide chain of globin. So CO2 not bind with oxygen. Okay, it is one of the ways that CO2 are transported in our blood. One of the ways where the CO2 can transport in our blood. Okay, this is normal. So we're talking here normal. But carboxyhemoglobin is kind of pathological form of hemoglobin. Yani sick. Okay, this carboxyhemoglobin, we can say there is the CO, carbon monoxide, will bind with the iron. Bind with the iron, displacing the oxygen. Displacing oxygen prevent hemoglobin from carrying oxygen. This is prevent hemoglobin from carrying oxygen. Okay, here is, so what happened now? We say affinity of hemoglobin for CO is higher than the affinity of oxygen 200 times. Here is one tricky point, guys. I say again, carboxyhemoglobin, carbon monoxide bind with the ferrous, displacing oxygen, because you know in oxygenated the oxygen bind with the ferrous, displacing oxygen and prevent hemoglobin from carrying oxygen. Yes, it's okay. And also this will increase the hemoglobin affinity to oxygen. Here is some question come from many sources. We know that CO, we're talking about hemoglobin. affinity to CO is higher than hemoglobin affinity to oxygen by 200 times. Okay, so here we understand this, but I say also CO can increase hemoglobin affinity to oxygen. Aha, so the hemoglobin affinity to the oxygen will increase. Yes, what does it mean? It means that even CO will replace the oxygen, the remaining oxygen in the hemoglobin will be attracted very strongly to hemoglobin, so hemoglobin cannot give that oxygen to the other tissues. So even you replace some oxygen and the remaining oxygen in the hemoglobin became very attached to the hemoglobin. So hemoglobin doesn't pass the oxygen to the other tissues. Methemoglobin. Methemoglobin, it is the oxidation of ferrose. So here is the oxidation of ferrose. So methemoglobin, you say that the ferrose is oxidized to ferric acid. Okay, this happened why, guys? This happened by what? By many of oxidizing agent our body are facing. You are going for many oxidizing agent, for example, to oxidize the ferrous to ferric acid. You know the patient, you can know the patient from his face. Dark color, cannot carry oxygen, small amount of methemoglobin, methemoglobin can be corrected. Yani if we have methemoglobin with a small amount, we can correct it by a specific enzyme. You will know it. You will need to know in the biochemistry. It's called NADH methemoglobin reductase. So if you have some of it, but if you have more from that format, you will have a very sick pathogenic form of methemoglobin. Okay, we have something called hemoglobin glycosylated. Hemoglobin glycosylated, you know, usually we say the people, they are diabetics, for example. We ask for them, please, when you come to make a diabetic analysis, go to make hemoglobin glycosylation, because you know when the sugar in our blood is increased than normal, the extra sugar will bind with hemoglobin, and this will make glycosylation of hemoglobin. So when you need to make like screening for your patient about the last 3 months, what about the diabetic, what about the sugar in the blood last 3 months, here is the best thing you can do. Because normally the normal value for this one is from 3 to 6%, but if that value from 60 to 10%, it means for last 3 months, that patient has high glucose than normal. You know, usually diabetes people, before they go for the doctor, they stay 1 or 2, 3 days, they are regulate them eating. Yani they say, okay, we can regulate our food. Yani. So you go for the doctor make blood test and he found glucose is normal, but I need to get an idea about the last 3 months. So last 3 months I will analyze the amount of glycosylated hemoglobin. If that amount increase above 6, it means your blood has more than normal glucose last 3 months. For that we have this glycosylated ratio is getting increased. Why last 3 months? Over 3 months, because you know the normal time for RBC is 120 days. So last 3 months is 90. So with this we know that RBCs which stay 90 days, how is the hemoglobin situation here? Okay, it's not pathological. The pathological, what you should know, carboxyhemoglobin, methemoglobin, and hemoglobin glycosylated is not pathological. It's happened normally with the percent 3 to 6, but if it is a percent over 6, it means that you have more diabetic. Kind of screening, we do it. Okay, up to this, guys, we can know that hemoglobin exists in 2 conformational states. Hemoglobin can found in 2 states. Some state is called the T state, tension, and one is relaxed state. T and relax. T state, it is deoxy form of hemoglobin. And you can see here is one hemoglobin. One hemoglobin 4 subunit, here is saturated, totally saturated hemoglobin. Here is called R state, relax. Why relax? Because I have my own oxygen. I have my own oxygen. So while T state, it is deoxy form of hemoglobin. It means it lacks an oxygen species and is also known as deoxyhemoglobin. So deoxyhemoglobin, this one is deoxyhemoglobin. This one is oxygenated hemoglobin. So the R state is a fully oxygenated form, oxyhemoglobin. What we studied here, oxyhemoglobin R. When I give that oxygen to the tissue, I became T, tense hemoglobin. Okay, so we make a relation between the saturation of the hemoglobin. You can see one hemoglobin, one oxygen was one hemoglobin, 2, 3, and 4. And I make that relation of saturation with the partial pressure of oxygen. We measure the gases as a partial pressure. We measure the gases as a partial pressure. Okay. People think that hemoglobin has a fixed affinity. And when I'm talking about the affinity of hemoglobin, you are thinking, or most of the students, they think that we have a fixed value for the hemoglobin affinity. No, affinity of hemoglobin is dynamic. What does mean dynamic? The affinity of hemoglobin will change up to the partial pressure of oxygen. And I give you example, guys. Let me try to handle it here, because this is the most tricky part here, and we finish up to here. Guys, you know the blood vessel is this kind of, let me do like this one. Our blood vessel, you know, we have veins and we have arteries, and usually we bring, here is the lung, here is the lung, just to make it easy. Here is our lung. And let's say here is our tissue, guys. Let's say muscle, for example, something like this. Okay. So guys, if I'm asking you in our body, where is the highest oxygen concentration? In the lung. So here in the lung, you have high partial pressure of oxygen. Yes. Why? Because usually lung, I make inspiration to get oxygen, so I fill my lung with the oxygenated air. And in the other side, the tissues which use the oxygen to make a metabolism, like muscle, producing a lot of metabolites, especially CO2. So we have here what? High CO2 and low oxygen. Okay, and our blood are traveling here. You think the blood close to the high oxygen has the same affinity like blood close to the low oxygen? Of course no. Hemoglobin is good guy. He is good guy. What does mean he is good guy? It means that hemoglobin going to the arteries closer to the lung, where the high oxygen will get high affinity to oxygen. It is a good chance I'm going to the open buffet oxygen. Open buffet, I eat. So what I mean now? I mean that when hemoglobin going to the area, go to the tissues, where is the high oxygen, it is a good chance for hemoglobin to attract more oxygen, to eat enough oxygen, because that hemoglobin will travel to go where? To go the tissue where is the low oxygen. At the low oxygen, hemoglobin is good guy. What does mean good guy? Hemoglobin will have low affinity. So what does mean low affinity? Low affinity, I give oxygen. So hemoglobin closer to the lung get oxygen because its affinity high, and the closer to the tissue where they need oxygen, I give oxygen because affinity is low. So this kind of affinity is not fixed, it is dynamic. For that, guys, when we have high partial pressure of oxygen, what about, look for the black curve, what about the hemoglobin saturation, maximum saturation? Maximum saturation, where we are here, we are closer to the lung. It's called the Bohr effect. So what is Bohr effect, guys? What is Bohr effect? Bohr effect, when I'm going to area, Halden effect, when I'm going to the area they have high oxygen, I will able to have more affinity. Area has high oxygen, more affinity. Area where is low oxygen, less affinity. High affinity means I get oxygen, less affinity means I give oxygen. So here is at the partial 180. What happened now? I have maximum. When the pressure reduced to 40, like in tissues, reduced to 40, what happened? Reduced to 40, I lose some of my saturation. I give one oxygen. So I move from 40 back to the lung. Here is 100, I get oxygen. I go there, here is 40, I give oxygen, and so on. So we can say now, in lung is 100, in tissue is 40 oxygen concentration. In lung where is high 100 maximum saturation, in tissue you are losing one oxygen. So you are losing 25 from your saturation. Yani we are not give the 4 oxygen. Usually hemoglobin only give 1 oxygen. Am I clear? Only give 1 oxygen. So here is the sigmoid curve of dissociation curve of oxyhemoglobin. At high partial pressure, high affinity. At low partial pressure, low affinity. Can you apply this in our body? Yes. Where we have high partial pressure, in the lung side, high affinity. I eat as much as I can oxygen. When I go for the tissue, we have a low affinity. Why? Because I should give the tissue 1 oxygen. It is kind of good character for hemoglobin. He is helping a guy. He helps us. When he goes to area where too much oxygen, he will carry it. When he goes to my tissues where they are poor in oxygen, they give to them. Here is the dynamic affinity. We have some factors in our body which can increase the affinity or decrease the affinity. For example, to know decrease or increase affinity, look for the point. And let's say choose one point here. I will make this line from here to here. Then I ask you, which point has more affinity? Point number 1 or number 2 or number 3? I need to know at this partial pressure, the point number 1 is less saturated. Point number 2 is that saturation. Point number 3 is that saturation. Where is the maximum saturation comparing between these 3 points? 1, 2, 3. 3. So we can say when the curve is shifted to left, shifted to up, it means I increase affinity. So the green one, it means high affinity, and this one low affinity. So when the curve is shifted to up or the left, increase affinity. When the curve is shifted to down or the right, decrease affinity. Okay. But what factor increase affinity? You think what factor? The most important factor, if there is high oxygen or no. If I have high oxygen, I increase the affinity, Halden effect. And increase oxygen means low CO2. Low CO2, high pH, and low temperature, and low diphosphoglycerol. So guys, you should know something here, guys. High pH is like low BCO2 and low temperature and low diphosphoglycerol. You think that tissues they have low temperature and the low diphosphoglycerol. What is diphosphoglycerol? It is kind of intermediates of the glycolysis. Yani, this means that tissue is not active in metabolism. Low temperature, low production of CO2, and low glycolysis. So that tissue need oxygen? No. doesn't need oxygen. So what I do, I have high affinity for to catch oxygen. The tissue doesn't need it because the character of that tissue is low CO2, low temperature, low glycolysis, means that tissue doesn't need oxygen. So I should have high affinity here. And the opposite, if I'm going to the tissues where is a high temperature, where is too much BO2, there is low pH, high diphosphoglycerol, that tissue means that character for that tissue means what? Means that tissue is high metabolite tissues, high activity tissues. So that tissue need oxygen. So the hemoglobin should have less affinity to oxygen to give the oxygen for that tissues. So decreasing affinity. This is called the Bohr effect, and when we have enough oxygen, called the Haldane effect. Haldane effect. What about these 2,3-diphosphoglycerol or biphosphoglycerol, bisphosphoglycerol? It binds to deoxyhemoglobin, and this one, when bind to the beta chain, beta globin. This one will make kind of interaction to facilitate oxygen release at tissue. Yani once this one bind with the beta globin, will decrease the affinity to oxygen. So the oxygen are released out. This make what? Stabilize tension form, yani make it tension form. Not saturated. Yani I give oxygen to the tissues. For that, when I told you that the fetus has more affinity because gamma cannot bind with 2,3-diphosphoglycerol, while beta can. So because the fetal hemoglobin, gamma cannot bind with 2,3-diphosphoglycerol, it has high affinity even if there is high 2,3-diphosphoglycerol. The high affinity of oxygen to bind to fetus hemoglobin due to the inability of gamma chain to bind to 2,3-diphosphoglycerol. I hope it's clear, guys. Enjoy it.